So this is an activated ring because of a dimethyl amino group, and this is a deactivated ring. So the disconnection would be here. Same, right? Deactivated ring with a different deactivating substituent. So if we were working backwards, we would want our precursor to be dimethyl aniline. And the diazonium salt of the sulfonic acid. Or the diazonium salt of the carboxylic acid. Because the activated ring is much more likely to be able to attack the diazonium salt than the deactivated ring. So then what we would need as a precursor, right, if we're working backwards some more, is we would need this. In order to make the diazonium salt. But we know how to make that, right? We've made that. We've taken aniline and protected the nitro group so we can put out sulfonic acid and deprotect the amino group. So that's a pretty easy compound to get at. Or, right, if we're working backwards from this one, we would want this. And that's called anthranilic acid. And that's great flavor. So there's tons of that available. You can get anthranilic acid. Once you have these, you can do the diazotization with this present, right? This one can't be diazotized because there's no hydrogens on those nitrogens to remove. So once that would attack a nitrosyl cation, the nitrosyl group would just fall back off. That equilibrium could never proceed forward. So the primary amine can be diazotized in the presence of the tertiary amine, and that way this will be there as soon as you form the diazonium salt ready to attack. Right? So that's the key when you're trying to make an azo compound like this, is you need to figure out which ring's activated and which one's deactivated, and you need the aniline derivative on the deactivated ring, and you need the activated ring to be the one that's actually going to be attacking the diazonium. So both of these compounds are readily available, right? Anthranilic acid is readily available. This para-aminosulfonic acid is readily available. And dimethylamine, or dimethyl aniline is very common. And I bet you could make both anthranilic acid and that para-aminosulfonic acid from benzene if you had cause to do that. EAS is code for electrophilic aromatic substitution, just so I don't have to keep writing out electrophilic aromatic substitution. So what can aromatic compounds do besides electrophilic aromatic substitution? Can aromatic compounds ever react with nucleophiles? The answer obviously is yes, or I wouldn't bring it up. There is a nucleophilic aromatic substitution reaction. Also referred to as ipso substitution, which takes a deactivated ring so if you have a compound that has a halogen on it and has nitro groups in the right place, I'm actually going to use fluorodinitrobenzene, because fluorodinitrobenzene Sanger's reagent. And is a reagent that's used in biochemistry to identify the N-terminal amino acid of proteins. And it does that by reacting with the NH2 group of the N-terminal amino acid. So if we treat this with a nucleophile, hydroxide or an amino group or something like that, let's just use ethylamine as an example rather than actual amino acid, so we don't have to draw out as many things. It can actually attack at the position where the fluorine is, which is referred to as the ipso position. And if we want to understand why it's so good, we need to actually draw out the nitro groups. It's important that the electron withdrawing substituents be the pi bonded type of electron withdrawing substituents. They need to be electron withdrawing by resonance. And they've got to be in the ortho and para position. You don't have to have both of them, right? Ortho or para, the more electron withdrawing substituents you have, the more favorable this reaction is going to be. So this differs from electrophilic aromatic substitution in that a nucleophile is attacking the benzene ring instead of the benzene ring attacking an electrophile. And it differs in that the thing that's going to be removed from the benzene ring is an anionic leaving group, rather than a hydrogen. Right, so we can attack that double bond because that double bond is electron deficient. And that'll put a negative charge in the ring. So the question is, why is that negative charge in the ring so good? And the answer is because I can put it out on oxygen. So I can actually draw a resonance structure for this that puts that charge all the way out onto the nitro group. And you can probably imagine that I could write a lot more resonance structures for that, because I could also put the positive charge or the negative charge here, and I could also put the negative charge there, which means I could get it out onto this oxygen as well. Okay. So there are three different positions in the ring that will bear that negative charge. The usual triangle can be drawn. And you can draw that kind of triangle in there and say, well, okay, the charge is going to be on the 2, 4, and 6 position. And that's why we need our electron withdrawing groups in those 2, 4, or 6 position, the ortho and para position, because we need to be able to take that negative charge that's in the ring and push it out onto the nitrogen, onto the nitro group, onto the oxygen atom of the nitro group. And if I were to draw this resonance structure, right, it would be obvious why that's where you want the negative charge. Because if you have the negative charge on one of these two positions, you can't get it out onto the nitrogen by forming that carbon-nitrogen double bond. Right. So it's a nucleophilic attack, first step. It's a really easy mechanism. just like electrophilic aromatic substitution, it's just 2 steps, nucleophilic attack, followed by that pair of electrons coming back in and kicking out your leaving group. That puts that double bond back on the nitro group. Proton transfer. Because our nucleophile was neutral in this case. If this were a peptide instead of ethylamine, what you would have done is you would have just tagged the N-terminal position with that dinitrobenzene group on there, and none of the other amino acids would have that dinitrobenzene group attached to them. So when you then hydrolyze the protein with concentrated hydrochloric acid to break it into its individual amino acids, one of them is tagged with a fluorescent label, a UV active label as well. So 3 steps: attack at the ipso position, push that pair of electrons out onto one of these resonance electron withdrawing groups, and then come back in and kick out your halide leaving group. And even fluoride will do this reaction, even though fluoride is not a great leaving group. It works. So nucleophilic aromatic substitution, aka ipso substitution, it's not limited to just the substituted benzenes. You can also do nucleophilic aromatic substitution reactions on some of the heterocyclic compounds. So if you had, for example, 4-chloropyridine, and you were to treat that with sodium ethoxide and ethanol, you could generate 4-ethoxypyridine, and you could probably show me the mechanism for that if I asked you to. Quiz on Tuesday. One more quiz before the exam. We'll have a review session next Tuesday in the evening. So what would you do if I asked you for the mechanism for this reaction? Hopefully the same thing we just did. Take that nucleophile attack here and push those electrons onto the electronegative nitrogen atom. Right, so the nitrogen atom in this case acts as the electron sink rather than an exocyclic nitro or sulfonic acid group. And then that pair of electrons can come back in and push the leaving group out to reform the aromaticity. So the second step is favorable on this reaction for the same reason that it's favorable in electrophilic aromatic substitution, because we regenerate the aromaticity. or we restore the aromaticity of the ring in the second step. So step 1 here is nucleophilic attack at the ipso position. And then step 2 is loss of the leaving group. And in this case, we don't have to have a step 3 because our nucleophile was negatively charged. And with a negatively charged nucleophile, there's no proton transfer step required to make the product neutral.